Okay, now we have Andrea Calcinari from the University of Sheffield who's going to tell us something about group field theory.
Yeah, so thank you for being on this side and to the organizers for letting me speak. So yeah, I want to talk to you about something that might sound technical, but in fact the upshot is very simple. So I want to talk about the notion of quantum states in a specific quantum gravity theory known as group field theory, from now on GFT. But what I want to focus on are like semi-classical properties of such quantum states. I am going to focus on the simplest scenarios. So in this GFT approach, we have pretty well established cosmological settings, and that's where I focus because everything is analytical and it's easy enough. And the question is, what should the state do? Because if you look outside, you don't have superposition of spacetimes, you don't have fluctuation. So I want to basically ensure that the theory allows for states that, too much, so that you can tame such fluctuations. So I'm going to very briefly tell about how this GFT cosmology paradigm gives you actually some emergent notion of cosmology and with quantum correction, so that's very nice. But then my work is on the notion of state. So I want to talk about what should be semi-classical state and why this is good or this is not good, for example, and I give you a few pure state as an example, and then I jump onto the general family which are called Gaussian states, look at their properties, and finally I hope to have time to actually show something which is a comparison. So the question I ask at the end is, what happens if I change the quantization scheme? So this, I think, is common in different quantum gravity theories. You can have a reduced phase space, or you can do a Dirac quantization, something like that. And indeed, in the at least looking at states, it seems to have a difference in this approach. So super briefly, this is a bit packed, but the idea, I'm going to be super naive and leave out many details because they're not necessary to see actually what I did. But the idea is that this GFT has a described spacetime as basically many particle states in a sort of quantum field theory way. So we have discrete building blocks, and we reduce the theory. So we look at the free theory, and in particular, I'm going to focus on the single mode. I guess I have a pointer. The single mode theory. So mode, you can think like Fourier mode. It's not quite a Fourier mode. It's basically the analog of that. And I'm going to couple gravity to a scalar field. This is now matter. Why do I do that? This is common practice because I need a relational variable. So it's going to be like my clock. And now what I do here is called parameterization because I choose the clock and then I quantize. And in the very end, at the very end, I hope to have time to comment on what if you change the setting. But in this case, like kinematically, I can build the Fock space, and without any details, what happens is that you do end up with the boson theory. So you have A and A dagger building, well, creating and annihilating quanta. But because of the GFT I started from, now the interpretation is geometrical. So I destroy and create quanta of geometry. Say, if I look at simplicial gravity, these quanta are going to look like quantum tetrahedra. But that's not a necessity. But in any case, the idea is that then geometry, like in the smooth sense, only emerges like in a many particle state, like this many excitation of such a underlying group. So I am in the parameterized approach, so I have a relational Hamiltonian, which is extremely simple if I am in single mode. And what does it do? Well, it actually evolves everything else with respect to my clock. For example, I define volume, which is crucial. What is the volume? It's just the volume of a single GFT quantum times the number of quanta. So this is naively the total volume. And I want to compare this with classical GR, where the volume is just the cube of scale factor. And what do I get? I'm jumping, obviously. This took some time, but now it's well known. And now we know that you can basically write down the volume satisfies a Friedman-like equation, which also has some quantum corrections that allow you to bounce. So indeed, this is now, this was very promising. It's already a few years old, and it motivates us to actually investigate what happens, because we indeed, so classically, you would have a Friedman equation in relational time that looks like this. So you have the v prime over v squared is a constant involving g. And now we do get that, provided that my GFT parameter is actually, related to the Newton constant, which is also nice because you can see g actually emerges from some more fundamental theory. But we have some corrections. They obviously disappear when the volume grows, but if the volume is still there, like at early times, you can show that this resolves the Big Bang singularity. But this is just the structure, the background. I want to focus on now, if you look closely, I have taken expectation values. And the question is, can I use any state? Are they important? Like, does that depends on it, and so on. And so let me jump to some more interesting stuff. I want the states to be semi-classical because of the things I've said initially. We don't really see fluctuations, and we don't really see quantum space-time. So the theory must be such that I can make them arbitrarily small. So this is the rest. So particular volume, which depends on kind, so it's evolving Hamiltonian. I need to make the relative uncertainty, so this is just the uncertainty, small. And also mention some other criterion, but I'm going to argue this is actually not crucial. So the idea is that in some even other theories, or in general, you see that semi-classical states should also minimize or saturate. Saturate, I mean, this inequality becomes an identity, the so-called principle, some other variation of this. I'm going to argue that this is actually not, even though this can happen, like if you pick an harmonic oscillator in Fock-coherent state, it's saturated, but it does not mean that this is like how you establish whether you can classify a state as semi-classical. So let's look at examples. Fock-coherent state, super simple. I'm going to also mention squeeze states, which are actually nicely related to like the group theoretical coherent state a la Paralamo-Gilmore, based on SU11 group. And in any case, let's see what they do in GFT. So super briefly, as I said, they don't necessarily, the uncertainty principle does not necessarily tell us whether they are semi-classical, because coherent states don't saturate this inequality at any time, but they are the stereotype of semi-classical state. And indeed, they work well for other reasons. And on the other hand, squeeze state minimizes such an inequality at all times. So this might be tempting to say the second state is the best, but it's not. So what I want to argue is that indeed there are much more important, such as the relative uncertainties, so the quantum fluctuations can be made small. So the question is, can I use the state parameter to make them as small as I want? This is a key question. And obviously, coherent states do the job. I guess I'm not going to read all of these ugly equations, but the point is that I can play around with the displacement parameter. I cannot, however, play around with the squeezing parameter. I decompose it like this. Because indeed, if you look, for example, at this line, neither the volume or the Hamiltonian fluctuations can go lower than 2, whatever I do with my R and psi and so on. And now I turn on time evolution, and the thing is the same. So even during time evolution, or specifically at late time, which is arguably the most important phase because it will be today, coherent state are good, and squeeze are not so good, that you don't have control over them. Just to show you what it means, if you plot this stuff in time, you can make the blue line go as low as you want. You play around, but you can't do much with the red line, which is the squeeze state case. Which means that the theory still depends on the coherent state. There's no other state. One question is, does it actually need the coherent state, or can you generalize that? So what I'm going to do, I introduce Gaussian state in the usual sense. So this is well known in quantum information, QFT, quantum optics, and so on. There's a bunch of properties, and what I found most useful is this theorem that when you have second-order Hamiltonians, you can always express a Gaussian state as a displaced squeezed thermal state. That's always the case. And obviously, this is quantum gravity state. It looks like what it does usually, but the interpretation is a bit, I don't want to push it too much because, for example, beta temperature, we're not sure, obviously, and there's some work on that, very interesting, on how to interpret such a statistical parameter. So now this is statistical ensemble. And I would also argue it could also be a chemical potential because it's right in front of the number operator. But again, for now, let's just do things for the sake of it. I mean, it's very hard to give interpretation in this case. But now the game is simple. So the expressions are going to be messy because the Gaussian state depends on 5 real parameters. So, it's a mess, but it's straightforward. Otherwise, it's a bit tedious. You can calculate everything, expectation values, variances, covariances, and if you don't like traces, you can use this thermal field dynamics, which is very useful and goes back to the 70s, I guess. And you also turn on evolution, and you basically check all the criteria that we have. So I'm going to flash you just for 1 second this, because again, the inequality is not saturated, but we know already this doesn't mean anything, and it's very much like the coherent state scenario. So not to worry, because even though the expressions are messy, you can calculate everything analytically and look at the quantum, relative uncertainties, and notice that they can always be made small. Now, I retain temperature, in quotation marks, and squeezing parameters, everything is in there. But because I also have displacement, I can basically still use the general family of states with 5 parameters, and I can check that I can make all of these expressions. I didn't show you the full time evolving picture because it wouldn't fit the slide, but the property is the same, but I can show you at least plots. Obviously, you can make bad choices, right? So if there's not enough displacement, you're not going to have very small fluctuations, and you can see an interplay of squeezing and stuff. But this is also true in the coherent state case. You can also make good choices. Obviously, the point is that you can play around with parameters or interesting choices. Like, for example, say we are at the late time, we don't even know if pre-bounds the universe was meant to be semi-classical. So this could be large, this could be tiny. You can basically play around. And this is the upshot. This is the main result in this approach, namely Gaussian states are super general and they still work. So the theory, it does not rely on necessarily using coherent state. Now, I think I do have time. Yeah, great. So this is intrigued. I think this is curious because now we change for a second approach, quantization scheme. So this is actually how GFT cosmology was born. So this is there's a lot of literature on this. Now the difference is that the field is now complex. And you postulate this. So this is not an A dagger now, and this is different chi's. So you postulate this bosonic commutator, and now similarly to what you do in a Dirac quantization, you build an abstract, if you like, kinematical Hilbert space with this phi and phi dagger, but it's still not physical. So this larger kinematical space is going to have a subspace which is physical, and what you do, imagine you're still doing Dirac quantization, you kind of impose a constraint, and you say psi is going to be physical if this constraint holds. Now, this is not always possible to solve, so one other thing you can do is look at the tower of Schwinger-Dyson equation. The first one would be just the expectation value of the usual equation of motion. Even if you do that and you find something, you can still say, on average, this is physical, and so you can make sense out of what follows. Now, this is super different from what I did before because until this point, I don't have any notion of dynamics, which only enters the game now. So what happens is that I use one of these conditions, and I find basically an equation for the state parameter, which now depends on chi. So this is basically what I had before. I called it alpha, but now I call it sigma just to differentiate the new approach. Sigma is basically the displacement parameter, but now it depends on chi, and it's through sigma that my volume is going to gain chi dependence. And magically, you look at the dynamics of this object, and it satisfies basically the same Friedmann equation. This is well known, and that's actually how it was born. But the question is, can I use a different state? Given that dynamics is implemented so differently, what happens? Well, I haven't done all I could, but I tried very hard, and it looks like Gaussian states don't work, and I think no other state seems to be viable. What happens is that you want to solve this, and for example, for the ones in the know, there used to be this dipole condensate state that don't seem to be physical, and also don't seem to give you small quantum fluctuations. And I showed the dipole case of Gaussian states, which also don't seem to be applicable because when you, for example, use this weaker statement, you still don't get any condition on the new parameters, say squeezing and temperature, but you only get a condition on sigma. So what you get out is the same Friedmann equation as usual with either constant new contribution or nothing new. So I think this is intriguing because you want at the end the two approaches to communicate. They should describe the same scenario, and obviously we need to further investigate this, and the states play a big role. So I'm going to give my conclusions there, but it's just a family of states, now a very large state parameter. They work well, small quantum fluctuations in the deparameterized approach, but some intriguing findings trying to connect the two approaches. This is still to be understood. Thank you very much.
Yep.
So about this thermal state on these group field theories.
Yep.
So normally in quantum field theory, of course, thermal states are heavily tied to to time via the KMS condition. Mm-hmm. Can you define something similar as a KMS condition in this context, as you don't really have
you can.
You don't really have a killing field or something, so.
So I think the most honest answer is you can, but I haven't done that. So I think these people have. So they have tried to push this interpretation and do basically exactly what you said. So make it formally like you do in QFT. I've been more naive and just wanted to calculate something new. But yeah, in fact, I think if I want to push, like if I want to give this a physical interpretation, I would have to go down that road. Yeah.
Do you know if they use modular operator theory or something like this to show this, or
I don't know.
Okay.
What they use now. Sorry.
Thank you.
Okay, let's thank our speaker again.